Share. Okay, so where we left off last time was we were about to start talking about the binary tree abstract data type. And so basically one of the fundamental things about binary trees that we sort of need to understand before we dive in too deep is how we can traverse the tree. When we say traverse, what we mean is visit every node in the tree, right? So we've talked probably about traversing an array or traversing a linked list. This means doing something to each element in the structure. So with the tree, it's a little more complicated. And we're going to have three different kinds of traversals that we're going to talk about. So let's study this for a second. This should make pretty good sense, okay? An algorithm that traverses a binary tree is going to be recursive, not necessarily, but typically. And the base case is going to be if T is empty, T being a pointer to the root. So here that's not stated explicitly, that's implicit. If this if statement is false, that's the base case, nothing happens. If the tree is not empty, then what we do is we display or process, however it is we're going to process the data in the root. And then we make a recursive call to the same function to process the left subtree. And then we make a recursive function call to the same function to process the right subtree. Everybody clear on how this little bit of code ends up? So I guess for now we can just focus on displaying the data. That's a good example, but just keep in mind in the back of your mind that this doesn't have to be just about printing. It could be about anything, that any sort of algorithm where we need to visit every node in the tree. Any questions about this pseudocode? Should make sense. So if you want me to talk about it more, just say so. Okay. And we'll be doing this when we write our own binary tree. But this form of the tree traversal is called a pre-order traversal because we process the root first before processing either the left subtree or the right subtree. So it's pre-order. We can also use in order, which we would get by simply reversing the first two lines, right? First traverse the left subtree, then display the data in the root, then display the right subtree. And then we could also do post-order traversals, which would just mean taking this display statement and putting it at the bottom of these three. And so it may not be, I'm sure it's a little fuzzy at this point what the difference is between those three, but it turns out to be super significant. And so we'll be talking about it at some length. All right, so the way the text in this part is organized is we're going to look at each of this each type of traversal one at a time. So here's just a slightly more formalized statement of the algorithm that we already saw. All right, so let's take a, yeah, I think what the way I want to do this is I want to take a timeout here, and let's just dive deep on looking at what the 3 different traversals are going to produce here, okay? So I have a little trick that I use when I am asked to tell what the results of a pre-order traversal are, or what the results of the in-order traversal are, and so on. So I'm going to show you that, but I also want to make sure you see how this is connected to the code for the 3 different traversals. So everyone sees these numbers in blue here, right? Those numbers indicate the order in which the nodes are going to be visited given this particular traversal. So what that means is that if we're always processing the root first each time, then we're going to, I keep going back and forth between process and display. I want to try to stick with just display for now. So we're going to display the 60 first, and then we're going to display the left subtree, and then we're going to display the right subtree. So displaying the left subtree means we're going to display the 20 first, and then we're going to display the 20's left subtree, and then the 20's right subtree. So displaying the 20's left subtree first, we display the 10. We're done with that. Now we display 20's right subtree. So we display the 40, then the left subtree, then the right subtree. Finally, we're all done displaying 60's left subtree. Now we go back up to the top and display 60's right subtree. So hopefully you can see where the 1, 2, 3, 4, 5, 6, 7 comes from there. The trick I use so that I don't have to think about the code at all, which I believe helps me avoid some mistakes sometimes, is that if you start at the top, at the root, and let's pretend we have a pencil, and we're just going, can I do that? Let me just play with this for a second. Okay, so let's say I start here at the 60, and I'm going to draw a shape around the entire tree, staying as close to the nodes as I can. And with a pre-order traversal, what's going to happen is we're going to display each node the first time we hit it. Okay, so I'm starting here, and so I display the 60, come down here, display the 20, come down here, display the 10, that's a little too thick. Okay, come back up here, already displayed the 20, now I'm going to display the 40, now I'm going to display the 30, now I'm going to display the 50, now I'm going to display the 70. Okay? So I'm not sure if that makes total sense the first time, but if you do it a couple times, I think it'll make sense. And it's pretty straightforward. Just first time you hit one of the nodes, you display it or process it. Okay, with in order, let's see if we can look at this picture for a second and understand how the numbers got there because of the code, right? So now what we're going to do is we're going to process the left subtree first, then we're going to process the root, then we're going to process the right subtree. Okay, so processing the left subtree first means I'm going to be displaying this subtree with 20 at the root first. So processing this subtree the first step is going to be to display the 20's left subtree. So the first thing that's going to get processed is this 10. Now I have processed the 20's left subtree. Now I process the root, so the 20. And then I process 20's right subtree. So this one here with 3 nodes. The process of processing that subtree is first do the left subtree, then do the root, then do the right subtree. Now we've done 60's left subtree, so now we're going to do the root, which is 60, and then we do the 60's right subtree, which is the 70. So hopefully that makes sense why these numbers come out in the order they do, processing the left subtree first, and then the root, and then the right subtree. But let me show you my trick. Let's try this one. The rule for my little trick for in order traversal is always process a node the second time you pass it. Okay, so I'm going to start here. I'm not going to, that's one time on the 60. That's one time on the 20. That's one time on the 10. Now you have to fudge it a little bit and say that I'm passing the, with the leaves, I'm passing it again on the way up. Okay, so now it's the second time I have passed the 10. So now I print the 10. Now I'm hitting the 20 for the second time. So now I print the 20. Ooh, that's my first time on the 40. That's my first time on the 30. There's my second time on the 30, so I process the 30. There's my second time on the 40, so I process the 40. First time on the 50. Second time on the 50, so I process the 50. It's my third time on the 40. My third time on the 20. Now finally there's my second time on the 60. First time on the 70. Second time on the 70, so process the 70. Okay? Anybody want to ask a question about that? I'm pretty sure this is the longest that I've ever spoken to my computer without any sort of feedback at all in my entire life. But that's okay.
Yeah, sorry.
No problem. No, I'm not complaining. I'm just observing. And I'm just making sure that you all
Makes
know
sense.
if something isn't clicking, feel free to let me know. Okay, taking a look at post-order traversal. So you can, so that's where you process the root last. So you process the left subtree, then you process the right subtree, then you process the root. So that explains why the root here has the number 7, which is the last number, right? So you can see how I'm processing the left subtree first, then I'm processing the right subtree, and then, so that's why this is a 6, and then the root, so that's why this is a 7. And then just analyzing this subtree here, I'm going to process the left subtree first, so the 10 is 1, then I'm going to process the right subtree, and then I'm going to process the root, and so on. If you like my little trick and you want to use it, then the rule is you process the node the last time you're going to see it. So once you get there and you see that you're never going to visit it again, you print it. So I start or process it. I'm still getting those words mixed up. I hope that's not too confusing. I'm using the words print and display and process interchangeably. Okay, so starting at the 60, still going to see it again, so nothing yet. Still going to see the 20 again, so nothing yet. Still going to see the 10 again, so nothing yet. Oh, now I'm passing 10 for the last time, so I process it. Hitting the 20, nothing yet. Still going to see the 40 again, nothing yet. Still going to see the 30 again, so nothing yet. Oh, there's my last time on 30, so now I process the 30. Hitting the 40 again, but it's not the last time. Hitting the 50, but it's not the last time. Hitting the 50 again, now that's the last time, so I process the 50. Now I'm hitting the 40, and I see I'm never going to come back to the 40, so I process the 40. Now I'm hitting the 20. I see I'm never going to process the 20 again, so I process the 20. Hit the 60, but I see that I'm going to hit it again, so nothing yet. 70, nothing yet on that side, but now I'm passing it for the last time, so now I process the 70. And then finally, now I'm passing 60 for the last time, so I process the 60. All right. Any questions about any of that? That's actually, that last 5 minutes is pretty important. You're definitely going to need to do that on your exercises. and probably on the quiz. So just make sure that that's something you can do. If I show you a binary tree and they say, what is the in order traversal of this binary tree? You should be able to do that with no problem in your sleep. Okay, so I think that was sort of a digression, and now we're going to go back to talking about pre-order traversals, though I should get rid of the annotation if I can. Can I just undo? Yeah, there we go. Thanks. Okay. So here's the code for in-order traversal. Like I said, you just process the left subtree, then visit the root, then process the right subtree, and then post order. Same exact code, just rearranging the order here so that we visit the node, visit the root last. Okay. All right. Oh, okay. Actually, I think there's a sentence from each of these sections that I passed over that I should have mentioned. So going back, if you apply a pre-order traversal to a binary tree that represents an algebraic expression, such as any tree in figure 15.3, and display the nodes as you visit them, you will obtain the prefix form of the expression. So that's a really important connection. If we go back to figure 15.3, how far back is that? Okay, here's our algebraic expression trees. Notice, let's take this one here. If I do, so what I have here is an infix notation, right? The kind of notation that we're used to. If I do an in order traversal of this tree, that's going to give me this expression, right? So in order was write it down when I'm passing it the second time. So starting here, first time on the A, second time on the A, so write the A. Second time on the minus, so write the minus. First time on the B, so write the B. I'm sorry. Second time on the B, so write the B. Second time on the slash, so write the slash. First time on the C, nothing yet. Second time on the C, write the C. Okay? So in order traversal of this expression tree results in the infix notation expression. Always going to happen. If I want to get the prefix expression, then I just do a pre-order traversal of this tree. So pre-order would be, it's kind of the easiest because you write it down the first time you pass it, right? So minus A slash B C. Minus A slash B C. So I know this is going back. You've probably all put prefix notation and postfix notation out of your brain. But if you can dredge it back up again, that's going to be super important. And so this is the prefix. This is converting this infix expression into a prefix expression. And the way this is all tied together is that you can do that same thing by doing a pre-order traversal of the expression binary search tree. Okay, and I could do the same thing over here, or I could do the same thing here again using postfix. But I think you get the idea. If I were to do a postfix, if I were to do a post-order traversal of this tree, I would get the postfix notation version of the original expression. All right, so I think that's kind of a cool connection, and hopefully we'll get that. Everyone will sort of get the connection there. Okay, my page won't, oh, there we go. All right, back down to where we were. So there's a sentence. If you apply pre-order traversal to a binary tree that represents an algebraic expression and display the nodes as you visit them, you'll obtain the prefix form of the expression. And then under in order, we have the same sentence, except for in order, right? Okay. If you apply in-order traversal to a binary search tree, you will visit the nodes in order according to their data value. Oh, sorry, that's not the same sentence. What I was thinking it was going to say is that if you apply an in-order traversal to a binary tree that represents an expression, then you're going to get the infix notation version of the expression. This is actually another interesting fact, though. If you apply in-order traversal to a binary search tree, remember, a binary search tree is just a binary tree where all of the nodes are in order, right? In order from smallest to largest. Just to do a quick review in case you've forgotten, all of the nodes in every node's left subtree are less than the root, and all of the nodes in every node's right subtree are greater than the node itself. If you're not clear on what a binary search tree is yet, that's probably not going to make a lot of sense, but just make sure you go back and get that figured out. Okay, looking at post order, let's find the sentence for post order. So here we have a similar sentence. If you apply post order traversal to a binary tree that represents an algebraic expression and display the nodes as you visit them, you'll obtain the postfix form of the expression. All right, any questions about all of that, all the connections? Okay. Not going to worry too much about this. So here's a question. What are the pre-order, in-order, and post-order traversals of the binary trees in parts A, B, and C of figure 15.5? That should be a link. Okay, figure 15.5. Let's go ahead and do this. Try to get a Word document down here. All right, so this is basically what you're going to have to do, not completely, but one of the things you're going to have to do on your assignment. So might as well just take some time to make sure we've got it. So looking at the binary tree in part A, pre-order would be A, B, D, E, C, F, G. So A, B, D, E, C, F, G. Any questions about that? Okay. In order traversal. So the second time I pass a node, I'm going to write it down, right? So that's going to be D, B, E. Now this is the second time I've seen the A. First time seeing the F, second time seeing the F, second time seeing the C, first time seeing the G, second time seeing the G. Done. Any questions about how I just did that? Okay, post order. So I want to hit it I want to write it down the last time I pass it. So D, E, still going to see A again. Oh, wait, sorry. Almost skipped the B. So here when I'm passing the B, that's the last time I'm going to pass it. So B, still going to see the A again, still going to see the C again. F, G, C, A. Okay. Any questions about how I got any of those three? All right. I'm going to assume, unless someone stops me and tells me otherwise, that we're okay with that and I don't need to do a bunch more examples. All right, let's get back down to where we were. Okay, binary tree operations. Test for empty, get the height of a binary tree, get the number of nodes in the binary tree, get the data in the root, set the data in the root, add a new node, remove the node containing the given data. So this is a not a position-oriented container, it's a data-oriented container, right? Retrieve a specific entry in a binary tree. Test whether a binary tree contains a specific entry, and traverse the nodes in a binary tree in pre-order, in order, or post-order. Okay, so we're not going to spend a lot of time on this. We're really focused on binary search trees. But it's good to know that those are the different operations that we could have if we were going to write a binary tree class. The assignment I'm going to be, when you get to your programming assignment, which is actually next week, no programming this week, you'll be working with a binary search, implementing a binary search tree, not a binary tree. By the way, I have to say I've been kind of toying with the idea that next time I teach this, I might combine the last assignment and this assignment, because there's really not that much work to do on this assignment, but 18 pages of reading, it's not too bad. Anyway, you can let me know if you have feedback about that. And don't just tell me to go ahead and do it because you want to get revenge on future students. Okay, so this is all just talking about the binary tree ADT. There's an interface template for a binary tree, which we're not going to be using. By the way, since I happen to see it, this right here is deprecated in C++ now, so you should not be having this throw statement as part of your function prototype. Anyway. Okay, binary search tree. We've talked quite a bit about it. So here's a binary search tree. Nothing too exciting here yet. Okay, binary search tree operations. Test whether it's empty, get the height, get the number of nodes. This is all related to the binary tree, right? Get the data in a binary in the root, insert a new item. When we insert a new item into a binary search tree, it's a little tricky, right? We have to be very careful that we put it someplace where it belongs, so that it's less than, if it's on any node's left branch, it's going to be less than that node, and so on. So we just have to make sure it's in a position so that the structure is still a valid binary search tree. I think I have already posted next week's assignment. Correct me if I'm wrong. Pretty sure I uploaded. I might have forgotten to update the.
It's up there.
Okay. Yes, I think I even suggest that you get an early start on it. Okay. So, kind of thinking it may be time to switch gears here. Yeah, let me just, let's switch gears. Give me, so basically what we're going to do now is I'm going to implement a binary search tree. Part of your assignment this next week, actually, I think all of your assignment, not all of it, but almost all of your assignment next week is going to be to just add some additional features to this class that we're developing now. But I will need you to give me a couple minutes here to get things set up. Okay, so here's a client program for a binary search tree class. This may look familiar. if I'm not mistaken, it is exactly the same as the client code for the simple list class that we developed earlier in the semester, except that it just says binary tree here instead of simple list. And same here. And then I think there might be, here's another occurrence, binary tree. Other than that, everything is exactly the same. So really what we're talking about here is, or at least one way to look at this, is that we are using a binary search tree, not so much as an ADT as we are an alternate implementation of a list. Okay, we have a list of numbers. All of the operations that we did on our original list of numbers, we're going to do on now on a binary tree. And really this should say binary search tree. Tempted to change it, but I'm afraid I will end up with a bunch of errors. So I'm going to leave it binary tree for now, but maybe at the end, if we have time, I'll switch it because it should say binary search tree. All right, so anyway, we can look at this and see some things we're going to have to write in our binary tree class. We're going to need a constructor. We're going to need a function named insert. We're going to need a function named print. By the way, let me just mention that's not typical for a container class to have a function named print. We're just putting that in there so that it's easy to debug. In a real life container class, you wouldn't have a print function. You would have some way to iterate over the structure, the container, and then the client would use that to do the printing. But we're going to do that just to make our life a little easier. We're going to have a size type. We're going to have a size function. We're going to have a find function, and we're going to have a delete function. And I think that's about it. The rest of this client down here is all about making sure that the assignment operator and the copy constructor work. Okay, so what I'm going to do is I'm just going to comment out all of this client code except for this part of it, which means all we're going to need is constructor, insert, and print. Okay. All right. Okay, so here's my header file. I've got a few things in here that we aren't going to need yet, so I will just comment them out. Okay, so this will look very similar to what we did with the list class, right? We've got a node declaration. In our list implementations, we called it node. Now I'm just going to call it tree node, just for fun. And the only real difference is when it's a list, it's linear. So it's got a data member, and then we have one pointer pointing to the next item in the list, right? With a binary tree, we're going to have data, and then we're going to have two pointers, one to the left subtree and one to the right subtree. That's pretty much all there is to it. Any questions about this, the header file code here? Okay. let's start working on an implementation file. So might as well just get things set up here. Okay, so let's do our constructor. Okay, so to represent an empty binary search tree, we're just going to have root pointer be null. I think I call it root actually. Yeah, root 6. Null pointer. All right, any questions about the constructor? All right, let's call print next. Okay, so here's a point at which things get a little bit messy. Okay, let's look at a binary search tree and talk about how print is going to look. Well, so we kind of know this. We saw the pseudocode several times in the textbook, right? It's going to be something along the lines of if the tree is not empty. I want to do a pre-order traversal because it's a binary search tree, and so it'd be nice to have them just printed in order, right? So I'm going to first print the node, the root. Then I'm going to call print with the left subtree. And then I'm going to call print with the right subtree. The problem is this. This function does not have access to any pointers, right? All it has access to is the calling object, which is a binary tree object. So it's not going to be possible to make this function recursive because let's take a look at something here real quick. Maybe this will help me articulate better. So here's just a picture of a binary search tree, right? So when I'm printing, what I have is this variable up here, source, is a binary search, in my case, we're calling it binary tree, unfortunately. The type of this variable is binary tree object, right? And the data member inside a binary tree object is a pointer to the root of the binary tree. But all of the rest of these nodes here, they don't have binary tree objects pointing at them, right? They just have other nodes pointing at them. So it's not possible to make the function we were just looking at recursive just the way it is. So what we're going to have to do is we're going to call an auxiliary function, and that function is going to be recursive. And that function is going to take a parameter that is a pointer to a node. Okay, so let me just go away for now. Well, what I'm going to do inside my print function, and this is going to be the pattern for every recursive function, how can I say that? Every tree recursive function is going to have to follow the same pattern. All I'm going to do in this function is I'm going to say print args, and I'm going to send it the root. Now we can have a print args function that has a node pointer as an argument, and so that one can be recursive. All right, so let me just say that if none of that made any sense at all, it's probably okay. Obviously, you'd like to have it make sense at some point, but if you just sort of follow the pattern, you'll be okay, right? If you can't, if you can't go down and explain to your friend why this can't be recursive, you can probably live with that as long as you just know that it can't, and you're going to have to write an auxiliary function. I guess if you really want to be clear about it, right? Try writing this function as a recursive function and see how it goes. Okay, so let's work on that auxiliary function. And yes, I am going to have to make this a member function of the class, but let me do that in a minute. Oops. Okay, so now is where I do my recursion. I'm going to say if the tree is not empty, first I'm going to I'm pausing because in my notes I have it as an in order traversal, and I'm not sure why I would do that, but I'm going to go with pre-order. So I'm first going to print. Oh wait, okay. Let me back up. Somehow my brain just went totally haywire. That's right. In a binary search tree, if we want the nodes to come out in order, we need an in order traversal, not a pre-order traversal. So I'm just going to leave it at that. And if you need a little review of that, you can check out that part of the text again where it listed we went through the different sorts of traversals. But I just got mixed up about that. So we want an in order traversal. So first I'm going to call print args on the left subtree. Then I'm going to print the root. Then I'm going to call print args on the right subtree. That's it. There's my print function. Let me save this. Should be here. Okay. Now let's talk about how to declare this in my header file. So it's going to be private, right? It's not going to be something that the client is going to call directly. What do you think about that? You guys are back to seeing my whole desktop, right?
Yep.
Okay. Yeah, now actually I just noticed in my notes that I don't have this const, but it should be. Okay, change it over here too. Okay, so I'm not sure if that's the constness that you were referring to.
I
But
think both can be, right. It can be a const function, and it can have
right,
const.
so we're not going to be changing the calling object, so we could put const there, but I'm going to go a step further with that. Really, this function doesn't need to access the calling object at all, right? It doesn't need to have a calling object, really.
It could be static.
Exactly. So we have we may not have done this before in this class, but one option we have is that we can make this static. I think the static comes first. Okay, so we haven't talked much about this, I don't think, and probably that's something we should hit on more than we do. But basically, putting static in front of a member of a class means that there's not going to be a separate one of these for each object. There's just going to be one that is shared by all objects of the class. In the case of a static function, that just means that you don't need to have a calling object when you call it. You can just call it like it was a global function. All right, so I'm going to go with that for now. I guess we have used the word static before when we had a constant in our class, right? And that makes sense. Constants in classes should be static because we don't need to have a separate copy of that constant for every object. We just need to have one constant that all objects of that class can access. Anyway,
I don't think it can be const now, though.
Yeah, exactly,
yeah,
right.
I messed up, sorry.
Yeah, no, that's okay. So, right, since we don't have a calling object, it doesn't make sense to have const there. All right, so I don't want to get too hung up on the whole static thing. That's not really the main point that we're trying to get across here, but hopefully that's not too confusing. And it would work if we didn't make it static, right? It would still work if I made it, if I just left it. It would just be awkward, I guess, that we have a function that's a member function, but it never accesses the class object or the class data members. Okay, so let's get going with our insert function so we can actually have something to test here. And let's go back and take, can you guys see the binary tree diagram okay? Okay, so let's talk about inserting an object into a binary search tree. For example, if I was going to insert the number 35 into this binary search tree, where would I put it? The number 35. So one option would be I could start moving nodes around, right? And just totally restructure the tree. But my question is, if I leave all of these nodes exactly the way they are, where's the 35 going to have to go? The answer is, it's going to go down here to the right of the 30. And I've already got too many nodes here, so I'm not going to actually draw it, I don't think, but we would put it down here to the right of the 30. Does that make sense why that's where the 35 would go? So, and here's one way of looking at that, okay? I'm going to look at the 40 and I'm going to say, okay, I'm inserting a 35. It's not going to go in 40's right subtree. It's going to go in 40's left subtree because it's less than 40. And I come over here and I say, okay, I'm inserting 35. That's going to go in 20's right subtree because it's bigger than 20. So I follow the arrow down here. I get to the 30, and now I have null pointer, so I know that I'm going to be inserting the 35 on this node's right. Okay, so every time we add a node to a binary search tree, we're going to be adding it as a leaf at the very bottom of the tree. It's not necessarily, I suppose, that we have to do it that way, but it's the easiest. You don't have to rearrange anything else. If we had time, if we had 1 or 2 more weeks of the semester, we would study a chapter called Balanced Binary Search Trees, or something close to that anyway. And then we would talk about how we might, instead of just inserting it as a leaf each time, do some rearranging of the tree to make sure that the tree doesn't get too unbalanced. But anyway, that's a different issue. Everyone understand that we're always going to insert new nodes at the bottom of the tree as a leaf. And the way we do that is we just follow the arrows down until we get to where it goes, right? So that's going to be what the insert function is going to look like. Nope, that's not it either. All right, so void binary tree colon insert. And I'm just going to call insert augs and send it the root and the item that's going to get inserted. Okay, then we're going to have binary tree insert augs. Same, not going to be constant because we're actually going to be changing it. In fact, we're going to have to make it pass by reference. Still got the item. Okay. Have you seen this before, star ampersand, in this class? So I guess if it's the first time you've seen it, sometimes it freaks students out a little bit. My advice about that is just separate them out and think about them one at a time, right? So if I have this, what I have is I have a root, a parameter named root, and that parameter is of type pointer to tree node, right? But now I'm saying I may want to change that and make it point at something different. For example, so if I'm inserting something and it turns out to be that I'm inserting it at the root, that means I'm going to be changing the root from what it used to be pointing to something different. So I need to make that pass by reference. Any questions about why it's star ampersand? Okay. Okay, so in this function, the base case is the hard part. The recursive case is the easy part. So I always like doing the easy part first. If root equals null pointer, that's when I'm going to actually have to insert a new node at the bottom of the tree. So if root is equal to null pointer, that means that in our picture, we're at the bottom and we have calls for, so for example, if we were inserting a 35, we got down to the 30 and we called insert augs with this node's right pointer. So what that means is, okay, we've reached the bottom. Now it's time to insert the node. Okay, so I guess I'll just go ahead and do this hard part first. We need to create the new node. and make root point to it. Okay, so that says, well, this looks like let's change this to 35 and then we've got it. Okay, so that means create a new node. No, that's not gonna work either, sorry. Forget about this picture down here. Create a new node. I haven't put the 35 in yet, but here's the part that I know a lot of students have a hard time visualizing. But at this point, root, this variable here, root, is this node's, the 30 nodes, right pointer, right? Because it was a recursive call. We called it with 20's right pointer. We got into the recursion. We found out that we needed to make a recursive call with 30's right pointer, and 30's right pointer is null pointer. So we're saying, okay, instead of having it be null pointer, make it point to this new object. Okay. Whatever. You get the idea. Oh, there. Okay. So that's the picture after this first statement here. Root gets new binary tree node. Second thing we're going to do is we're going to go ahead and put the data in there. So root arrow data gets item. So that means this is going to get 35. Okay, and just ignore this down here. So now what we need to do is we need to just set the 35's left and right pointers to null pointer. Okay, so that's it for actually adding the new node. We're done. Now that was the base case. Now we have to just say, whoops, else if item is less than or equal to the roots data. Then we're going to call this function again with roots left subtree. Otherwise, we call it again with roots right subtree. Okay, so just to review what's going on here, we're saying if root is null pointer, that means we've made it all the way down to the bottom of the tree. So we're going to make root point to a new node that has the item in it. If root is not equal to null pointer, that means we haven't reached where we want to insert the item yet. So we're going to say, okay, if the item is less than root arrow data, insert it into root's left subtree. If the item is greater than root arrow data, insert it into root's right subtree. Any questions about this code? Okay, so we still need to add it to the header file. think that looks good. All right. Anything else we need to do before we can test this? I think we're good. I'm going to comment out this because otherwise it's going to give me a warning message about not using the variable. Shall I try it? So, what did I call the client? Tree client. All right, let's see what we got here. What? Did I type that wrong? Ooh. Try that again. All right, I probably have other errors, but I'm just going to try it again. Active close curly brace. Line 29, line 37. To match
Maybe it's
1 and line
below.
29. Hold on. Open, close, open, close, open, close. And so what was that? Maybe it's what?
Nope, it's there. I just wanted to see below.
Oh, let me try again. One of them. And in the trees. I just hit save again, so maybe before I had
Yes.
not hit save when I was done. Okay, and then we can insert numbers. And then when we're done, they'll get printed out in order. All right, any questions about that? Okay. I'm thinking that's a good stopping point. So next time what we'll do is we'll finish up. We just have size, find, and delete. But if you guys want to get an early start on the assignment, all of this is there's videos where I do all this, and there's actually not a great lesson, but the code is all posted. So, all right, any last words before we go? All right, have a good weekend. I'll see you on Tuesday.
Thank you, Dave.